In July 2026, an Orca extra-large unmanned undersea vehicle completed a Pacific transit of more than 1,000 nautical miles. The U.S. Navy called it a first for the program. That is roughly the sea distance from London to Rome, traveled by a machine with no crew at the controls. But the most interesting part is not the distance. It is the environment. Satellite navigation is extraordinarily precise above the ocean. Below it, the signal almost vanishes. Radio becomes unreliable. A small error in speed or heading grows with every hour. So how can a robot submarine know where it is, decide where to go, and arrive without a human navigator? The answer is not one magic sensor. It is a layered navigation system that constantly measures, predicts, checks, and corrects itself. A GPS receiver works by timing faint radio signals from several satellites. In air, those signals can cross thousands of kilometers. Seawater is different. Because it conducts electricity, it absorbs high-frequency radio energy extremely quickly. Move only a short distance below the surface and ordinary GPS signals are effectively gone. A submarine can rise high enough to expose an antenna and obtain a position fix, but that interrupts the submerged mission and may reveal its presence. Public reporting does not say how often Orca surfaced during the 1,000-mile transit. What matters is the engineering problem between any external fixes. Once underwater, the vehicle must carry its position forward from the last known point. That process is called dead reckoning, and it begins with a beautifully simple idea. Measure every movement, then add those movements together. Imagine starting from a surveyed point and moving east at 4 knots for 1 hour. The estimate says you are 4 nautical miles east, but what if the speed sensor is wrong by only 1%, or a current quietly pushes the vehicle sideways? The position on the computer and the position in the ocean begin to separate. Dead reckoning error accumulates because each new estimate starts from the previous estimate. Over a long passage, tiny biases can become kilometers. This is why a robot submarine cannot simply point itself at a compass bearing and run a timer. It needs instruments that measure rotation and acceleration, sensors that observe motion relative to the seabed, and software that understands that every measurement has uncertainty. Navigation is not a dot on a map. It is a dot surrounded by an expanding cloud of possible error. At the center of the stack is an inertial navigation system, or INS. Gyroscopes measure how the vehicle rotates. Accelerometers measure how its motion changes along 3 axes. Starting from a known position, the computer integrates those signals to estimate attitude, velocity, and position. It is self-contained, fast, and silent. It does not need to transmit anything. But an INS has a weakness. Integration also accumulates sensor bias. A microscopic error in acceleration becomes an error in velocity, then a growing error in position. Better instruments drift more slowly, but none are perfect. Boeing publicly says Orca combines a Kalman filtered inertial unit with Doppler velocity logs and depth sensors. That sentence reveals the core architecture. The INS provides the continuous prediction. Other sensors periodically restrain the prediction before it wanders too far. A Doppler velocity log, or DVL, acts like an underwater speedometer that looks down. It sends several acoustic beams toward the seabed. When the echoes return, their frequencies have shifted slightly. The shift is the Doppler effect. Echoes from the direction of travel are compressed, while those behind are stretched. By comparing the beams, the computer estimates velocity in 3 dimensions relative to the bottom. This is valuable because it reveals motion the inertial system might misjudge, including sideways drift. The geometry also provides altitude above the seabed. DVL is not a universal answer. If the bottom is too far away, the acoustic lock can be lost. Suspended material and rough terrain can degrade measurements. But whenever reliable bottom track is available, it gives the navigation filter a powerful independent check. Now the measurements must be combined. An inertial estimate updates quickly but drifts. The DVL observes velocity, yet its echoes can be noisy or disappear. A depth sensor knows vertical position, not latitude and longitude. A GPS fix, when available, is absolute but intermittent. A Kalman filter treats navigation as a cycle of prediction and correction. First, it predicts the next state using the vehicle's motion model and inertial data. It also predicts how uncertain that state should be. Then a new measurement arrives. The filter asks how trustworthy that measurement is compared with its prediction. A clean DVL return pulls the estimate strongly. A noisy reading moves it only slightly. The result is not perfect knowledge. It is the statistically best estimate the system can make, together with an explicit measure of how uncertain that estimate has become. The seabed can become a map. An echo sounder measures the distance below the vehicle, while stored bathymetric data describes the expected shape of the ocean floor. As the robot crosses ridges, valleys, and slopes, software can compare the observed depth profile with the map and search for the best match. This is called terrain-aided navigation. It is most useful where the topography has distinctive features. A flat, poorly mapped abyss offers fewer clues. Boeing also lists bottom following and seabed mooring among Orca's design behaviors, but it does not publish the exact algorithms or sensors used in the 2026 transit. So the correct conclusion is careful. Bathymetry can provide another constraint in a long-endurance navigation stack, while the precise Orca implementation remains undisclosed. Knowing where you are is only half of autonomy. The robot must also decide what to do next. A mission planner supplies waypoints, depth limits, safety boundaries, and rules for unexpected conditions. The guidance layer converts the next objective into a desired heading, depth, and speed. Controllers move fins and propulsion to follow those commands. Meanwhile, health monitors watch batteries, temperatures, leaks, sensor quality, and communication status. If a sensor disagrees with the others, the vehicle may reject it, slow down, change depth, return to a safe point, or surface according to pre-programmed rules. Those exact Orca rules are not public. What is public is the design goal: autonomous operation in open and congested waters. In practice, that means the system must manage uncertainty, not pretend uncertainty does not exist. Underwater communication obeys the same physics that blocks GPS. Ordinary radio has little reach, so long-range links usually use sound. Acoustic messages can travel kilometers, but they are slow, delayed, and vulnerable to noise, reflections, and changing water conditions. Sound moves through seawater at about 1,500 meters per second, roughly 200,000 times slower than radio and air. Available data rates can be tiny compared with Wi-Fi, and many acoustic links are effectively half-duplex. Optical systems can send much more data, but only over short, clear water distances. This rules out joystick control across an ocean. A useful XLUUV must execute the mission locally, then exchange compact status messages or data products when conditions allow. Communication supports autonomy. It cannot replace it. Navigation only matters while the vehicle has energy. Boeing describes Orca as a hybrid system with batteries and marine diesel generators, and advertises a design range of up to 6,500 nautical miles. That number is a manufacturer specification, not the distance independently demonstrated in the July milestone. Conceptually, batteries power the vehicle during quiet submerged operation. At suitable moments, a diesel generator can replenish stored energy when it has access to air. The public material does not reveal the transit's exact charging or surfacing cycle, so we should not invent one. The engineering challenge is to schedule propulsion, sensors, computation, and charging while protecting a safe energy reserve. Every extra knot costs power. Every detour costs range. Route planning is therefore also energy planning. Orca is more than a navigation experiment. Its baseline vehicle is about 15.5 meters long, and Boeing describes an optional 10.4-meter modular payload section capable of carrying up to 8 tons of dry payload. The interfaces can supply power and communications to different mission packages. That turns the vehicle into an undersea truck whose middle can change while the navigation core remains the same. Public Navy documents call it a multi-mission platform, but they do not identify the payload carried during the Pacific transit. The important engineering idea is modularity. Propulsion, energy, guidance, and vehicle health form a reusable backbone. Mission equipment can be integrated separately. Proving long autonomous transit makes that backbone more valuable because any future payload depends on reaching the operating area reliably. The 1,000-mile transit does not prove that Orca can perform every mission, survive every failure, or remain submerged for that entire distance. The Navy has not published the route, duration, navigation error, sea state, intervention level, or surfacing schedule. What it does prove is narrower and still important. An Orca vehicle completed a long autonomous Pacific transit, a first for the program. Round the world, Australia is developing Ghost Shark, Britain is experimenting with Excalibur, and France is advancing a large autonomous combat undersea demonstrator. The strategic race is global because the engineering advantages are compelling. endurance without crew fatigue, risk without people aboard, and persistent access to areas where communication is poor. But every one of those advantages depends on the same quiet question: can the machine still know where it is? Underwater, navigation is the foundation of autonomy.